Welcome to the lecture series on CFD Part 2. This is lecture 28 on solution methods for compressible flows. This lecture starts with a brief introduction to compressible flows and pressure correction methods for all Mach numbers. Next, the Implicit Fractional-Step Method, IFSM, for the computation of flows at all Mach numbers is described. Fractional step methods for incompressible flows were presented in lecture 17. Here it is shown how such methods, and in particular the implicit version, can be extended to be applicable to both incompressible and compressible flows at all Mach numbers. The following set of slides is devoted to the simple algorithm for the computation of flows at all Mach numbers. Simple and related methods for incompressible flows were presented in lecture 18. Here, the extension of such methods to compressible flows is described in detail. Most commercial and public CFD codes use such methods when computing compressible flows. Next, coupled solution method for the computation of flows at all Mach numbers are briefly described. They have some advantages compared to the methods just mentioned when computing steady-state flows. Commercial CFD codes ANSYS Fluent and Simpson-Testa CCM+ offer such a solver, which also works for both incompressible and compressible flows. Finally, the application of simple and coupled solver in Simpson-Testa CCM+ software for invested flows around an airfoil at different Mach numbers, subsonic, transonic, and supersonic, is presented to demonstrate the main features of these solution methods. Compressibility effects are important in many flows, for example, in aerodynamics and turbomachinery applications. Many methods were specifically designed for the computation of compressible flows. They usually obtain density from continuity equation and pressure from an equation of state. Methods designed for compressible flows are usually not efficient when applied to flows at very low Mach numbers. Many flows of practical interest contain zones of both high and low Mach numbers. It is therefore desirable to have a method which is efficient in all flow regimes. In the late 80s and early 1990s, several such methods have been developed and published. 3 of them will be briefly described. To compute compressible flows, it is necessary to solve not only the continuity and momentum equations, but also a conservation equation for the thermal energy and an equation of state. In compressible flows, viscous dissipation may be a significant heat source, and conversion of internal energy to kinetic energy, and vice versa, by means of flow dilatation is also important. The complete energy equation has the following form. On the left-hand side, we have the rate of change of enthalpy per unit mass, H, in the control volume and its convection flux through the control volume surface. The first term on the right-hand side is the conduction defined by the Fourier law, that is, by the product of the thermal conductivity K and the gradient of the absolute temperature T. Next comes the volume integral of 2 terms. The first is a scalar product of the velocity vector and the gradient of pressure, and the second is the scalar product of 2 tensors, the viscous part of the stress tensor, S, and the gradient of velocity vector. This is the so-called dissipation function, a non-negative quantity involving the product of fluid viscosity and squares of velocity gradients, describing the irreversible conversion of kinetic energy to heat. For a perfect gas with constant specific heats, Cp and Cv, the enthalpy becomes H equals Cpt, allowing the energy equation to be written in terms of the temperature. For a perfect gas, the equation of state is P equal rho RT, where R is the gas constant. The complete set of equations to be solved, in addition to the thermal energy equation and the equation of state, includes the mass and momentum conservation equations given by these expressions. Here, T is the stress tensor, including pressure terms, and B represents body forces per unit mass. See lecture 3 for a discussion of various forms of these equations. The nature of the pressure depends strongly on the flow type. While in incompressible flows only pressure differences matter, In compressible flows, P is the thermodynamic pressure whose absolute value is of critical importance. In open domains, pressure must be specified on part of the boundary, while in closed domains, the initial pressure defines the absolute level. Let us now see how the implicit fractional step method, or IFSM, which was described in lecture 17 in slides 12 to 14 for incompressible flows, can be extended so that it can be used to efficiently compute also compressible flows. At the mth outer iteration within the new time step, we are solving the momentum equation of the following form for the estimate of the new time level solution. Here, V star is the predictor value for Vm. It needs to be corrected to enforce continuity. The second order, fully implicit free time level scheme for time integration was used. Note that the rate of change term is also nonlinear because it involves products of density and velocity, and both are now variables. Because particular spatial discretization schemes are not important here, symbolic notation is used for convection fluxes, C, diffusion fluxes, L, and gradient operator, G. In the end, we need to require that the corrected velocity and pressure satisfy this form of the momentum equation, in which the velocity in the rate of change term and the pressure are updated, with the aim to enforce the mass conservation. By subtracting the first equation in the preceding slide from the second one, we obtain the following relation between velocity and pressure corrections. Here, the velocity correction is defined as Vm minus V star, and the pressure correction is defined as Pm minus Pm minus 1. The discretized continuity equation is not satisfied by rho m minus 1 and V star, representing the solution at the time level m plus 1. A mass imbalance results. We require that the continuity equation is satisfied by the corrected density rho star and the corrected velocity Vm. The blue framed parts are now updated. In the last equation, rho star is an estimate of the density at outer iteration n. The final value will be computed at the end from the equation of state after Tm is computed by solving the energy equation after the mass and momentum equations are solved. We now introduce the density correction, rho prime equal rho star minus rho m minus 1, and expand the product of corrected density and velocity as follows. The underlying term, being the product of two corrections, tends to zero faster than other terms and is neglected from here on. By subtracting the two last equations from previous slide from each other and considering the above expansion of the product of rho Vm, the following expression is obtained. Velocity correction can be expressed via pressure correction as shown in slide 8. To obtain a pressure correction equation, we need to express the density correction also via pressure correction. How this can be achieved is shown in the next slide. The link between density and pressure corrections is obtained from an equation of state. Density is in general a function of pressure and temperature. To relate density correction and pressure correction, we express the density correction as the derivative of density with respect to pressure times pressure correction as follows. The partial derivative of density with respect to pressure is denoted as C rho. It depends on the equation of state. One can now rewrite the last equation from the previous slide as follows. This is the pressure correction equation for flows at all Mach numbers. It resembles a transport equation for a scalar variable. It has the rate of change term, convection term, diffusion term, and source term. Upon solving the above pressure correction equation, velocity, pressure, and density are corrected to obtain Vm, Pm, and rho star. These values are used in the next step to solve the energy equation, from which the updated temperature Tm is obtained. After all transport equations are solved, the final density at the outer iteration m, rho m, is computed from the equation of state based on Pm and Tm. After a sufficient number of outer iterations is performed, all corrections become negligible, and we can set Vn plus 1 equal to Vm, Pn plus 1 equal to Pm, Tn plus 1 equal to Tm, and ρn plus 1 equal to ρm, and proceed to the next time step. In the limit of an incompressible flow, that is, Mach number equal to 0, the left-hand side of the pressure correction equation becomes 0, and we recover the Poisson equation derived in lecture 17, slides 10 to 14, for incompressible flows. In the limit of a high Mach number flow, the rate of change in the convection term becomes dominant, and the pressure correction equation resembles the continuity equation. Let us now see how one can extend the simple algorithm derived in lecture 18 for the computation of incompressible flows to compressible flows at all Mach numbers. In the first step of the new auto iteration M, the momentum equation is solved for V star equal Ui star vector II, whereby the density, pressure, and fluid properties are taken from the previous iteration M-1. The superscript indicating this lag by one auto iteration is omitted from here on for clarity. The coefficient matrix is split into the main diagonal AD and an off-diagonal part AOD, as described in detail in lecture 18. Upon solving this equation for Ui star, we require that corrected velocity field satisfies the following form of the momentum equation when the pressure is corrected. Density is left unchanged at the level ρm-1. The corrected pressure P star is defined as the pressure from previous auto iteration Pm-1 plus correction P prime, while the corrected velocity is defined as the velocity obtained by solving the above equation plus a correction U prime. We then subtract the first equation from the second one to obtain the relation between velocity and pressure corrections as shown by this expression. These steps are the same as in the case of incompressible flows. The velocity correction is proportional to the gradient of pressure correction. The discretized continuity equation is not satisfied with ρm-1 and V star. A mass imbalance results at the right-hand side of the equation. We then require that the continuity equation is satisfied by the corrected density ρ star and corrected velocity Vm, as indicated by this equation. Here, ρ star is an estimate of the density at auto iteration M. The final value ρm will be computed at the end from the equation of state after Tm is computed. We define the density correction as ρ prime equal ρ star minus ρm-1 and expand the product of corrected density and velocity in the convection term as follows. In this expression, only the corrections ρ prime and V prime are unknowns. The last term, being a product of two corrections, is neglected because it tends to zero faster than other terms. The relation between density and pressure corrections is the same as described in slide 10, given by this expression. By inserting relations between velocity and pressure corrections defined in slide 12 and density and pressure corrections defined above, leads to the following pressure correction equation. It resembles a transport equation for a scalar variable. It has the rate of change term, convection term, diffusion term, and source term. The left-hand side is the same as in IFSM, see slide 10. The diffusion-like term and the source term on the right-hand side may be different. C rho is determined from the equation of state. For a perfect gas, the following relation is obtained. The coefficients in the pressure correction equation depend on the approximations used to approximate the gradients and self-phase values of the pressure correction. The part which stems from the velocity correction, diffusion-like, is identical to that for the incompressible case. This part requires an approximation of the derivative of pressure correction in the direction normal to self-phase and should be approximated in the same way as the pressure terms in momentum equations. The part which stems from the density correction corresponds to the convection flux in other transport equations. It requires an approximation of the pressure correction at the self-phase center. Methods described in lectures 7 and 8 can be used for this purpose, but there are many special approximations in literature designed to better capture shock waves and avoid non-physical oscillations in pressure and velocities. Some approaches are described in section 11.3.3 of the book and references therein. For an incompressible flow, the pressure is indeterminate to within an additive constant. The presence of convection terms in the compressible pressure correction equation makes the solution unique. The diffusion term is of order 1 over Mach number squared relative to the convection term. Thus, at low Mach numbers, the Laplacian term dominates and we recover the Poisson equation. At a high Mach number, highly compressible flow, the convection term dominates, reflecting the hyperbolic nature of the flow. Solving the pressure correction equation is then equivalent to solving the continuity equation for density. The pressure correction method thus automatically adjusts to the local nature of the flow and is applicable to the entire flow region, even if it contains both high and low Mach number zones, for example, in a flow around a bluff body. The coefficient matrix for the pressure correction equation is not symmetric in the case of a compressible flow, contrary to the case for incompressible flows. This means that some solvers for linear equation systems, which are especially efficient when applied to equation systems with a symmetric matrix, cannot be used for the pressure correction equation if the flow is treated as compressible. The third class of solution methods applicable to flows at all speeds are coupled solvers using special preconditioning methods. One such coupled method, which is used in commercial CFD tools, has been published by Weiss and Smith in 1995 and in an improved version by Weiss et al. In 1999. The method uses preconditioning of the time derivative to make it applicable to incompressible as well as to compressible flows. The coupled system of conservation equations for mass, momentum, and energy is solved by matching in pseudotime. The solution variables are pressure P, Cartesian velocity components Ui, and temperature T. Note that pressure does not feature in the continuity equation. It is introduced in it through the preconditioning. The preconditioning matrix K, which multiplies the terms with a time derivative in the coupled system of equations, is shown in the next slide. This is the preconditioning matrix, which multiplies the rate of change terms in the coupled system of equations. For example, the rate of change term in the mass conservation equation is multiplied by theta times the time derivative from continuity equation plus delta rho by delta t times the derivative from the energy equation, and so on. The derivative of density with respect to temperature is taken at constant pressure. For an ideal gas, one obtains the following expression. Delta in this term is set to 1 when the flow is treated as compressible, while for an incompressible fluid, both delta and delta rho by delta t are set equal to 0. The most important parameter is theta, which is defined as given by this expression. UR in the last equation from previous slide stands for a reference velocity, which is selected such that the eigenvalues of the system with respect to convection and diffusion timescales remain well conditioned. This is achieved by limiting UR in such a way that its value nowhere falls below the local convection or diffusion velocity. The third limiting value in this expression is chosen for reason of numerical stability, especially because of stagnation point or line zones. Epsilon is a constant, typically set to 10 to minus 3. Delta x is the local length scale for diffusion based on grid spacing. For compressible flows, UR is additionally limited by the local speed of sound, c. This couplet solver is available in SimSynthetasis Plus software, which is a second-order finite volume method. The preconditioning of the time derivative destroys the time accuracy. To compute a steady-state flow, matching in a pseudotime is used until the time derivative becomes 0. To compute an unsteady flow, dual time stepping is used. Equations then include a derivative with respect to physical time and a preconditioning time derivative with respect to a pseudotime. For every physical time step, several steps in pseudo-time are taken until the solution stops changing, that is, a steady state in pseudo-time is achieved. The steps in pseudo-time correspond to outer iterations in the sequential, also called segregated, pressure correction schemes described earlier, simple and IFSM. The implicit Euler method is used for integration in pseudo-time because large time steps can be used, and the aim is to obtain a steady-state solution, so temporal accuracy in pseudo-time is irrelevant. For the physical time, a time-accurate integration scheme is used with time steps appropriate for the given flow, for example, leading to physical CFL around 1. Let us now see how the coupled solver and simple algorithm perform in some examples representative of external aerodynamics applications. We are solving Euler equations, that is, in viscid flow, for the steady-state flow around an airfoil at free far-field Mach numbers. Subsonic flow with Mach number equal 0.6, transonic flow with Mach number equal 0.8, and supersonic flow with Mach number equal 1.2. Two solution methods in SimCenter Plus software are used for each test case. Sequential, in the software called segregated, solution of pressure correction equation derived from the mass conservation equation, simple algorithm, momentum equations, and energy equation, and a coupled solution of preconditioned equations with a vector of unknowns p, ux, uy, uz, and t. The efficiency of the two solution methods when computing steady-state and viscid flow is analyzed. The same test cases will be revisited in lecture 32 for turbulent flows using the runs approach. We are first looking at the subsonic flow around an asymmetric airfoil at 0 degrees angle of attack and the Mach number in the far field of 0.6. That is, we are expecting a subsonic flow in the whole solution domain. The plot shows the polygonal 2D grid around the airfoil. The solution domain is larger, shown is only the grid near airfoil. It is locally refined near airfoil surface and in a box surrounding airfoil, and then gradually coarsened with distance from airfoil where the flow does not differ much from the far field uniform flow. These two plots show the polygonal 2D grid close to the airfoil and a zoom near leading edge. Because the flow is viscid, thin prism layers near airfoil wall are not absolutely necessary, but we generated them because the same grid will be used in lecture 32 for turbulent flow computation, where prism layers near wall are important. The airfoil chord length is 1 meter. The velocity field is initialized with the far field velocity corresponding to the selected Mach number. Pressure is initialized with environmental or atmospheric pressure. These plots show the computed distribution of Mach number, pressure, temperature, and density around the airfoil. The velocity reduces to 0 at the front stagnation point, where the pressure has the maximum value. The velocity increases rapidly along the front part of the airfoil suction side, and then gradually reduces along suction side toward the trailing edge. On the pressure side, the velocity reduces gradually from the leading edge to the trailing edge. The pressure is lowest where the velocity is highest, as was the case in incompressible flows. Because the density is proportional to pressure via equation of state, its contours are similar to pressure contours. Temperature contours are also similar to pressure contours. The free stream temperature was set to 300 Kelvin. We see that the temperature increases up to circa 22 degrees near front stagnation point and reduces by circa 28 degrees at the suction side where maximum velocity is obtained. The pressure contours are smooth everywhere, but in other variables we see disturbances downstream of the trailing edge. These are due to discretization errors and become smaller when the grid is refined. Here, second-order linear upward scheme was used to approximate convection fluxes. Disturbances would have been much larger if the first-order upwind scheme was used. This plot shows the variation of pressure coefficient along airfoil surface, computed with the two solver versions. The results from coupled solver and simple algorithm are not identical because the computation of mass fluxes is slightly different. The differences are very small except at the trailing edge. The marked points are related to disturbances seen in contour plots in the previous slide. The other three plots show residual histories of the coupled solver and different time steps in pseudotime, here expressed via the CFL number 10, 100, and 1000. In this subsonic flow, all variables vary smoothly and one can use large time steps. 4 times less iterations are needed if the CFL number is increased from 100 to 1000, meaning a 10 times larger time step. These three plots show residual histories for 3 sets of under-relaxation parameters in the simple algorithm. The rate of convergence becomes higher as the under-relaxation factors for velocities and temperature are increased. However, with the highest values tested, the normalized residuals stop reducing after about 800 iterations and then remain constant around the level of 10 to minus 5. This happens often when second and higher order schemes with limiters are used. This is not a problem if residuals stall at a sufficiently low level, as in this case, because iteration errors are then lower than discretization errors. This can be verified by monitoring some integral quantities of interest. This figure shows the variation of lift coefficient with iterations. It is obvious that after about 500 iterations, the value does not change anymore, and that it was smoothly converging toward the finite value from almost the beginning. In the case of transonic flow, with a far-field Mach number at 0.8, 2 shocks appear in the flow, one on the suction side close to the trailing edge, and one on the pressure side close to the leading edge. The existence of these shocks can be seen in the simulation performed on the same grid which was used for subsonic flow, but they are not well resolved. However, one can use the solution on a coarser grid to identify the zone which requires further refinement. Here we use 2 rectangular zones to specify a significantly finer grid resolution with the aim of resolving the shocks better. The grid is then regenerated, the original solution is interpolated onto the new grid, and the computation is restarted. These 3 plots show the contours of Mach number, that is, velocity scaled with the speed of sound, pressure, and temperature around the airfoil for Mach number 0.8 in the free stream. The maximum Mach number reaches about 1.66 at the shock on the suction side near trailing edge. Temperature increases by almost 40 Kelvin at the leading edge and drops almost 80 Kelvin just before the shock on the suction side. As in the subsonic case, disturbances in velocity and temperature are visible downstream of the trailing edge due to discretization errors. The 4th plot shows the variation of pressure coefficient along the airfoil surface. From the maximum value at the front stagnation point, pressure reduces smoothly along the suction side and reaches the lowest value just upstream of the shock. On the pressure side, the reduction of pressure coefficient is initially very steep, followed by a plateau before the shock. Thereafter, pressure coefficient increases toward the trailing edge. At the far field around the airfoil, pressure is everywhere the same, equal to the atmospheric pressure. Also, pressure at the trailing edge must be the same when approached from suction side and from pressure side. This shock is needed to raise the pressure to the level required by the downstream condition. The convergence of iterations in the coupled solver was rapid and smooth in the case of subsonic flow, even with very high CFL. But in the case of transonic flow with 2 shocks, iterations are not converging at all for CFL equal 1000. With CFL equal 10, convergence is smoother but rather slow. With the simple algorithm, convergence is both smoother and faster than with coupled solver, using the usual under-relaxation factor for steady-state flows, 0.8 for velocities, 0.2 for pressure, and 0.9 for temperature. In the case of a supersonic flow at the free stream with Mach number 1.2, 2 shocks are present in the flow field. One is circa half a chord length ahead of the leading edge, and another on the suction side right at the trailing edge. Simulation was again first performed using the grid shown in slide 22, and then locally refined in zones where the shocks were identified. These three plots show predicted contours of Mach number, pressure, and temperature. The Mach number reaches a maximum value of 2.14 ahead of the shock at the trailing edge. The temperature rises by 86.5 Kelvin at the leading edge and reduces by almost 100 Kelvin ahead of the shock at trailing edge. The pressure coefficient varies smoothly along both suction and pressure sides of the airfoil. At the trailing edge, pressures are equalized through the shock on suction side. As in the two previous cases, small disturbances are seen at the trailing edge. The temperature field shows also small disturbances along the two shocks. The SimCenter StarSystem Plus software offers also the option of an automatic selection of the CFL number. This leads to a fast reduction of residuals by 3 orders of magnitude, but after that, all residuals oscillate nearly periodically around a steady level. In the case of simple algorithm, the residuals drop rapidly by 2 orders of magnitude, then gradually another 2 orders of magnitude, and stall at that level. The history of drag and lift variation with iterations suggests that converged values are reached after circa 2000 iterations. Here is a summary of this lecture. Solution methods developed for incompressible flows can easily be extended to handle compressible flows as well. The pressure correction equation obtains the rate of change and convection term when the flow is compressible. The coefficient matrix for the pressure correction equation is then not symmetric. The ratio of convection to diffusion contribution in the pressure correction equation is proportional to Mach number squared. In the limit of incompressible flow, that is, when Mach number equal to 0, the Poisson equation is recovered, as in incompressible flows. A couplet solver, which solves simultaneously for the vector ρ, ux, uy, uz, and t, works also for flows at all Mach numbers when an appropriate preconditioning of the time derivative is used. All solvers converge slower when shocks are present in the flow. This is due to the fact that approximations of second and higher order produce oscillations in solutions at shocks, which need to be damped by suitable limiting. See chapter 11 in the book and the references therein for details on limiters and special shock capturing schemes.